Okay.
So it's my mic. Okay.
Yes.
There is echo. Who was a speaker? Moit. Right. Okay. So in case of strong disorder, don't have Bragg glass. Lesner phase is ridiculously small because the penetration depth is enormous, and you have mostly a vortex glass that can resemble this kind of distribution of vortex spacing, where you barely see no translational order, roughly some hexagonal or triangular piece of lattice, but the rest is very disordered. This is a glass system. And it turned out that the physics of this vortex glass have been studied a lot in the vortex matter, but mostly the transition to the normal state. This has been widely investigated in transport, making IVs and scaling and many things. So lots of things have been done. This is the story of thermally assisted flux flow or creep, and this is widely understood. There is something which is less known, which is the nature of these vortex states at t equals 0. And even the question whether the vortex states can be superfluid is a question, and it depends also on dimensionality, of course. And if it is superfluid, how evolves the superfluid density of a vortex glass as a function of magnetic field? All these questions actually are not known. This is annoying. I will stay here. And another question which is of importance, and that brings me to the superconductor-insulator transition, is the disorder dependence. So I say we are at strong disorder, but you may know that at some level of disorder, we kill superconductivity. And this is a quantum phase transition, and one can wonder how this vortex glass evolves to these dramatic events where we kill superconductivity. So I just remind you what is the superconductor-insulator transition, which is pictured by this iconic phase diagram proposed by Matthew Fisher quite some time ago in 1990. This is the basic phase diagram of a 2D superconductor. You have temperature, magnetic field, and this delta here is disorder. It's not the gap, so it's a bit confusing, but that's how it is. And you recognize in the temperature disorder plane standard decrease of TC with disorder, to energy scale because it's 2D, you have a Berezin crystal transition, whatever. And you have a quantum critical point where superconductivity is destroyed. And if you look at t equals 0 on the disorder magnetic field plane, you have this vortex glass phase, and this quantum critical point is somehow pulled all along to 0 disorder and form a line of quantum critical transition, quantum phase transition. Right. And the question I want to address, and I will address in this talk, is how the vortex glass evolves when you start from low disorder and you increase the disorder and look how your properties evolves at different value approaching the critical point. I want to give you just a glimpse of how it looks in magnetotransport. This is the whole story in the field of disordered superconductor. If you apply perpendicular magnetic field to a disordered field, here is a set of magnetoresistance curve, resistance versus magnetic field at various temperature, the same field. You see that the resistance is quite large, of the order of kilo ohm, and what you see is a relatively straightforward and standard transition to the normal state. And the evolution of the curves follows what we expect for thermally assisted flux flow and all this activated behavior of vortices. So this would correspond to a film which is, say, at very moderate disorder. Now, if I increase the disorder in this material, what happens is the following. The resistance is increasing substantially, and surprisingly, the critical field is decreasing to lower magnetic field, which is opposite to what we know in standard superconductors, because usually when you increase disorder, Hg2 increases. And most importantly, you have a shoot of the magnetoresistance, a peak that appears just after the transition, just at the transition to the normal state. Now, let's approach even more the critical disorder. What happens is a dramatic transition to a gigantic insulator state that you see here, which form what was called in the field the Cooper pair insulator, which I don't show here. There have been several evidences that these states is formed with Cooper pairs. People have made tunneling. There is a superconducting tunneling gap which resembles the superconducting gap of the superconducting phase. People have seen little part effects, coherent effects related to superconductivity. And in addition, you see that this peak dies out at a field which coincides more or less to the low disorder Hc2, which would indicate a pair breaking mechanism at high field. So I love these curves, and I would like just to emphasize the fact that if I take this data and repeat it just a little bit, this is one of the most spectacular quantum phase transition I'm aware of. Perhaps I'm a little bit biased, but this is a transition you can tune with changing very little magnetic field. Here, the transition is super sharp and actually super difficult to capture experimentally, because you need to measure two infinites, infinite conductivity and infinite resistivity. And we see here we reach our noise level, but here we are not at the noise level in conductivity, because insulator you need to measure in voltage and superconductors in current bias, which makes the measurements easy. Okay, all right. You may wonder what is the material that gives all these characteristics. This material is amorphous indium oxide. This is a very well-known material in the field and actually in the society, because if you put a little bit of tin in this material, you get the famous ITO that you all have in your tooth screen, which is this transparent conductive electrode. And if you keep only indium and oxygen, you get an amorphous material which undergoes a metal insulator transition and also a superconducting to insulating transition that is captured here with this series of films where you see the Tc decrease as a function of the resistance. For those who are not in the field, just want to point out that the disorder we are considering here is insane. Resistivity reaches 1 to 20 milliohm centimeter. You have very little superconductor that can exist with such a resistivity. There isn't actually one example is very underdoped LSCO cuprates that reach these values and is still superconducting. If you are still not convinced this is very disordered, I want to show you this curve that I like in semi-log, exactly the same data. And here I placed with a PowerPoint superconducting transition of aluminum. And you can see that you have 4 orders of magnitude difference in disorder between our conventional superconductor and these disordered superconductors. All right. Now let's go to the vortex matter and the vortex glass business. How to characterize the vortex glass? I showed you magnetotransport properties, but this is a little bit boring because this is thermally assisted flux flow, and we don't probe really the vortex state. Vortex state is superconducting, so how to probe it? And the best way is actually to measure the superfluid stiffness of the vortex system. How we do that? So just to remind you, what is the superfluid stiffness? You all know that. This is the elastic energy cost with the phase of the superconductor. And one way to measure it is via the kinetic inductance of the superconductor. There are other ways, like measuring the penetration depth with 2 coils inductive measurements. Here, what we do in our measurements is a direct measurements of the kinetic inductance, which, as you see, is proportional to the resistance of the film, so disorder, and inversely proportional to the gap of the superconductor. And the superfluid stiffness is simply given by the flux quantum square proportional to 1 over LK. For circuit people, this is a very well-known formula. This is nothing but the Josephson energy, or for SIS Josephson junction. You see that when the critical current is small, EJ is small, and the stiffness is small, so you very quickly twist the phase across your junction or across your superconductor. So we use a modern technique compared to simple magnetotransport. Modern technique to measure the superfluid stiffness. We actually measure the kinetic inductance of superconducting resonators, which are made by coupling a strip line of indium oxide to a transmission line where we pass microwave through. And if we know the capacitance of this object, this strip line, we can very simply, from the resonant frequency of this resonator, get back to the inductance. And if we apply a magnetic field, if you apply a magnetic field, you just get the capacitance is independent of magnetic field. So what you can measure is the inductance as a function of B, and the superfluid stiffness is just proportional to the frequency square. This is very straightforward and powerful method to measure the superfluid stiffness at t equals 0 as a function of P. So I would like to start with actually a control experiment and investigate a low disordered material. And so it's not indium oxide, this is molybdenum germanium. Resistance of the film is about 100 ohms. We are 2 orders of magnitude lower in disorder than indium oxide. And this is the kind of data that we can measure when we look at the transmission of our sample and the resonance of the resonator as a function of magnetic field. You see that the magnetic field, perpendicular magnetic field goes up to 10 Tesla. What you see are resonances with harmonics. So these three things that decrease drops with magnetic field are one resonator, and you can even see a second resonator, which had a different coupling here in this sample, which is basically going along this shadow line. And you see that they all converge towards a critical magnetic field, which is actually the Hc2 of the matter. Now I can take one frequency as a function of B and square it, and I get the superfluid density, assuming I know the superfluid density at 0 magnetic field. I normalize it, and this gives me the evolution of the superfluid density as a function of magnetic field. I normalize it with this Hc, and what you see is a power law decay suppression of the superfluid density in this vortex state. So this is not a vortex glass here, and I'm going to show it to you. This is a standard vortex lattice, elastic lattice with spinning. And to show you that, we need to go into the physics of this of the microwave response of a vortex lattice. And the equations are not terribly complicated, actually. What you may expect when you shake a vortex lattice with microwave is the following: is a reduction of the kinetic inductance, or reduction of the penetration depth, right? Sorry, an increase of penetration depth. In the following manner, you have the zero field kinetic inductance, and the kinetic inductance increase with magnetic field linearly with B, and inversely proportional to the effective curvature of the pinning potential. This is very simple. You can make a check that if there is no pinning, the curvature is 0, this term diverges, and LK goes to infinity, which means that you don't have superconductivity any longer, because just the current with the Lorentz force moves all the lattice, and you have a voltage across your sample. So here the pinning is essential to maintain superconductivity in the sample. If you follow this limit of individual pinning of vortices, we expect a decay of the superfluid stiffness as 1/B. There are other models, collective pinnings, the elastic lattice, Bragg glass limit, and in that case, it is expected that the curvature of the pinning potential goes like 1/B. You plug that up, and you obtain something which is 1/B squared. And this is more or less okay with what we found in molybdenum germanium. So this molybdenum germanium is a good control experiment that show that we can measure the superfluid stiffness of the vortex lattice. It's consistent with the standard pinning picture, and this is a very nice probe for the vortex system, which is, by the way, never been done in that configuration so far. Now let's go to the vortex glass and to the indium oxide. You have crossover between
What?
you have crossover between isolated vortex and collective. Huh?
What you measure is the upper.
No, I
What is the thickness of this film?
I think it was relatively thin. It was relatively thin, a couple tenths of nanometers, but I cannot give you the right number. Okay, so let's go to the vortex glass and this very disordered material. Now the inductance goes to nanohenry per square up to 10 nanohenry per square. The superfield density is extremely small, below Kelvin. And here is what we get. So I show you the raw data. This is the same plot as before. You can barely see the difference, but still you see that there is a decay of the frequency, so an increase of the inductance. Here we have two resonators. Those are just the harmonics. This is a much more disordered sample. You see the critical field is 0.4. This is where there is this giant magnetoresistance. And now we can take several samples like this and plot the inductance, the square of the frequency, as a function of the normalized critical field. And what we obtain is this curve. Now it's different from molybdenum germanium because it's not a log-log plot, it's a semi-log plot. And what we obtain is a logarithmic suppression of the superfield density. What does it mean? It means that the superfield density is much more robust in this vortex glass than in the standard elastic lattice system. And if you want to see what we should expect for a collective pinning, if you put a power law, you would expect this. So which means that you see at this distance to the critical field, your vortex glass is super robust, super stiff actually, and it's super good. So how to understand this? This is where theoreticians comes, and Feigelman and Kavanagh invented a new type of vortex pinning, which is called interaction enhanced pinning of the vortex glass. And what they considered is that in such a disordered system where all vortices are pinned, the movement of the vortices are actually uncorrelated, which means that in a standard vortex lattice, you have pinning that try to fix the position and interactions that try to push the whole lattice and make transnational order. Okay, here the situation is different. Pinning makes disorder, but there is such a strong disorder that moving a vortex cannot move the whole lattice, and actually the surrounding vortices are nearly not moving, and the interactions tends to increase the pinning actually. So it's the total opposite to all what have been studied so far in vortex system. And here is a nice ChatGPT imaging where you see what you could expect in such a vortex glass. If you try to move this vortex, it will slightly move the neighbors, but not on long scale, easy. And this interaction will enhance the pinning. This is similar to the problem of the boson peak in structural glasses, where people have seen that you can have localized vibrational modes in glasses with a significant density of things. So you can make a little bit of hand-waving arguments if you want to calculate the curvature of the pinning induced by interaction. You just derive twice the interaction between vortices. The second derivative, you get 1 over x squared, you put that at a distance from the magnetic length, and you end up with a curvature which goes linearly with B this time. And if you plug it here, you get something which is where you kill this 1 over B component, and you end up with a prefactor to be determined. So this is where the theory stops, because it's a complicated problem. And Kavanagh and Feigelman made numerics, and it turns out that this is equivalent to a 2D Coulomb gas in a random potential, where in 2D interactions between charges are logarithmic, and solving dielectric response is equivalent to the superfield response of my vortex glass. And their simulation leads to this evolution of the superfield density, which is also logarithmic and goes as a function of disorder, the parameter. So the data are here. You see, if you cast all this data on this scale, it would end up here. if they would be able to go to lower, stronger interaction, they may reach our limit, but you see that it's totally consistent. There is a logarithmic suppression of superfield density in this superconductor. Okay, good. Few minutes, and I go to the consequences of that. You have seen there is a new regime of interaction-induced pinning of the vortex glass. And it has consequences for the superconductor-insulator transition and disordered materials. If I come back to this giant magnetoresistance peak, and I plot back-to-back superfield density and resistance measurements, what you see is here is two samples with two different BC, so different disorder. It diverges to megaohm, gigaohms, and the superfield density vanishes exactly at this transition to insulation. And very importantly, what you can see is that it vanishes linearly, which is super important for what concerns quantum's critical scaling of this quantum phase transition. And you can see that it coincides more or less with this transition. So the measurements have been done in situ on the same sample with the whole bar separated from the resonator, and there is a pretty good matching. And this is important because a couple of years ago, we studied in low disordered samples what was called the low temperature anomaly. Turns out that these disordered superconductors, they have always a small deviation of the HC2 to magnetic field. Some people study that in the context of the quantum Griffiths anomaly. And we looked in a different perspective. We looked at the critical current as a function of temperature, as a function of magnetic field here. And in this paper, we found a very unusual scaling. Actually, it was not unusual, but we found a scaling of the critical current as 3/2, which is actually the same as we expect close to TC. But this is the scaling you expect for depairing critical current in a mean field transition. And if you believe that you can have the same mean field behavior here, you expect, therefore, to have a superfield density that scales linearly with the magnetic field. And these measurements that I showed you of superfield density is a beautiful confirmation of this mean field behavior and explain why the critical current goes as an exponent 3/2. Also, one of the important consequences is that this mean field scaling is not compatible with quantum critical scaling that has been extensively used in this field to extract critical exponent. I'm not claiming any generalization of this story. This is perhaps specific to this material, but I think all the inconsistency in this kind of analysis perhaps call for revisiting this transition as a function of magnetic field in this indium oxide. Also, interestingly, you may have heard there will be a discussion this afternoon about failed superconductivity, which is when some people have seen that if you cool down in the mixed phase a 2D superconductor or thin films, the transition fails and you end up with a saturated resistance. This is an example of indium ion. This is indium oxide. Here you see it saturates at 1 Kelvin. You cannot go to the normal state, to the superconducting state. And this is totally not consistent with our observation that the vortex glass is superfilled. And we actually showed a couple of years ago with our colleagues at Columbia University in Weizmann that you can measure actually with good filtering and proper measurements a nice thermally assisted flux flow down to extremely low temperature in this material and also in molten charge. Okay. I give the credits to the two heroes who made this magnetic field dependence of superconducting resonators. David Perpont, who is now in Paris, Thibaut Charpentier, who is postdoc at UCSB, the new team now, which is taking over in Grenoble, and my two colleagues, theoreticians, Victor Kabanov from Ljubljana University and Pavel Mine, who is now located in Ljubljana. This is the conclusion, and I thank you for your attention.
Benjamin, so I think the important question is you have this at the critical field, your superfluid stiffness is going to 0. What do you have above the critical field? Is it a quantum vortex liquid?
The comfort is insulating.
It is insulating. The point is that you have the dissipative state with vortices down to t equal to 0. How do you characterize that state? Because we had a similar observation some years back, where we saw that the coherence peak in the spectra actually vanishes exactly at the same point.
You are aware, because you are in the field, that if you do tunneling, you still have the same gap that goes in the insulator. There are many evidence that electrons are paired in this insulator. The nature of this insulator is a big question. People even think that it might be a beautiful platform for many-body localization, for instance. I'm just stating that what happens before was just not known.
That is right. But
That's
the
it.
point is, there are many explanations like many-body localization for this insulating state. But would it be possible that this is just related to vortices, to a state of vortices as opposed to all these other complicated scenarios that have been put? Because now you are essentially looking at vortex responses in this system, which was not the usual way to look at it.
Well, okay, you asked me to give intuition, but my intuition always comes from results. Interesting, but from results. What I see is that the more you put magnetic field, the more you enhance spinning. So when you go to the insulator, you keep superficial stiffness, but at some point also spinning is enhanced. So if you want to have a resistive state, you need to move your vortices. Also, vortices are macroscopic classical object, right? They are cores. So if you want them to move at t equals 0, you need to remove the core states, perhaps. If there is a pseudo gap into there are plenty of speculation and discussion, and it's very.
What is your evidence that pinning is actually increasing?
That?
What is the evidence here that the pinning is actually increasing? Not clear, yes. So in standard elastic model, when you increase the magnetic field, the pinning is enhanced because Coulomb so vortex interactions is strict. So vortex interactions is reduced when we increase magnetic field. Here, what we say is the opposite, is that vortex interaction enhance the pinning. So in the calculation, they took into account self-consistently the screening of vortex interaction. How it evolves with magnetic field, actually, yes, sorry, perhaps made a wrong claim. I don't know how it evolves.
Okay.
Yeah, thank you. I have a question about you made the statement at the end that this scaling that you found would not be compatible with typical critical point scaling. I didn't get that point.
Yeah, we got mean field exponent. That's why.
Yeah, but there was a combination of values with
yes.
and so on, and it could be that they also add up to 0, and then you would have mean field scaling, isn't it?
So if D equals, so there's the question of dimensionality, which is always very delicate with these materials. So if D equal 2 by miracle, then you have C nu equal 1. This is the point. We got exponent 1, which is the mean field 1. Then this is not what was expected with what, if you want to compare with magnetotransport, Z nu is usually completely different. Actually, you can find a variety of Z nu in the literature, going from 0.8 to 2.3, or I forgot, variety of models, but rarely 1. And here it's 1, and it's compatible with the mean field critical exponent.
Well, after all, this is also an expansion of mean field, right?
Yes.
Anyway,
Okay. I'm sorry, I know there are other questions here, but I should delay it for the discussion.
Yes.
So thank you very much, gentlemen.